So where are we in our course? Maybe we'll have all the lights on so the camera gets. Okay. Yeah. So where are we in the course? We've completed a sort of semi-thorough study of the Bosonian string. I say semi-thorough because, well, it's been pretty thorough study of the technicalities of the Bosonian string. We haven't used it yet to do much business. Partly because it's hard to do physics with an unstable. Okay, and now we're trying to go over the description of all of the known superstring theories, known perturbable superstring theories, and we've ended our first brush with type 2A theory, type 2B theory, and type 1. I say first brush for two reasons. Firstly, we haven't yet studied interactions with these theories, strict scattering amplitude and so on. And secondly, sort of more importantly, we haven't tried to understand the physical questions. Both these things we will do soon. Okay, but before we get to that, what we want to do is to complete our run through of the thorough first run through of the spectra of supersymmetric string theories. Okay. So, we're going to start discussing the heterotic strings this lecture. Now, I'm going to follow, there are many different ways of presenting these theories, and as through the rest of my course, I'm following his textbook. So there are many other very nice discussions of the heterotic string, one of which is in the scope by Lust and Tyson, which is a very nice discussion. It's something from a slightly different point of view. Okay, so let's just following Wilczynski. Let's follow him and ask the question. Well, we've constructed various theories in the world sheet of the string. How can our constructions be generalized? Okay, so something that I have not emphasized enough, and we will when we in sigma model calculations, but I've not emphasized enough is that when we study the Bosonic string theory, though we studied for much of the time, we largely studied one example, namely the theory of the Bosonic string propagating in flat premises space. All our technical constructions go through for any unitary C equals 25 theory plus the free time theory coupled to the basis. Okay, so similarly, when we study type 2A and type 2B string theory, our constructions essentially go through when we replace any conformal field theory, the conformal field theory, by an appropriate superconformal field theory. Okay. The chief issue in these theories, the issue that distinguished these theories, was that perhaps the most important thing about string theory, about the string world sheet theory, apart from the conformal invariance of the world sheet string, is the issue of what states on the string theory are physical. And that is the issue of what constraint algebra you choose to gauge, equivalently what your BRST current is. So when we studied the Bosonic string, we chose to gauge conformal invariance, the conformal component. Okay? Equivalently, we wrote down a BRST current, which involved the stress tensor. Okay? When we studied the superstring, we've so far chosen to gauge the superconformal group. Equivalently, we wrote down the BRST current, which involved the stress tensor and the other TF, super stress tensor. Okay. Now, it will often happen that we study string theories where the world sheet theory is a lot of symmetry. But there's a crucial difference between the symmetries that just are there in the world sheet theory and the symmetries that we gauge. Okay? So it could be that the world sheet theory that we study has, instead of n equals 1 as superconformal invariance, has n equals 2 superconformal invariance. But I think type 2A and type 2B theory, we chose to gauge just n equals 1 part of it. So the other n equals 2 will be there and will be useful in some space-time questions, but will not determine, will not restrict the physical states of our theory. So these are the constructions we've done so far. And apart from conformal it's the most important structure that we emphasize is the algebra of symmetries that you gauge. It is the choice of gauging. Now, you see, in generalizing for the bosonic string, the superstring, what the key thing that we did was to change the algebra that we gauged from being the conformal algebra to the superstring. Now, something you might ask is, can we do some further generalizations? Now, other interesting algebras to gauge in the world strings that will give us a sense of notation. Okay? So let's start investigating that. Following questions. Let's start investigating that a little bit. In the next 5 to 10 minutes, I'll largely be just telling you some results. Well, telling you about attempts. You can ask, what is the full set of worldsheet algebras? Holomorphic worldsheet algebras. And the answer to that question is, of course, not known. It's not. These things are not classified. There are many symmetry algebras you can write down, some of which involve nonlinearities, in the sense that the stress tensor between two currents doesn't really just a current, but it will be a product of currents and these things. Okay? There are many different kinds of algebras one can write down. People have written out very complicated algebras, but no attempt to make a string theory based on anything very complicated is worked. Okay? The only things that give you something semi-sensible after a lot of efforts for various reasons that are far from incomprehensible are algebras where the symmetry current has maximum spin. And is always half. Okay, the symmetry current has some spin, that's always half. Okay. Now, symmetry algebras with both these properties written down, or with both these properties satisfied, are apparently sort of simple and easy to classify. Okay? And all these are symmetry algebras have been classified. Okay, so just to say it again, symmetry algebras which are generated by holomorphic currents of spins less than or equal to 2, all spins being integers or half integers. And when I say symmetry algebra, I mean the linear structure. So operator products of operators give you something linear. Singular terms are linear. If by symmetry algebra you mean something more complicated, because it's not been classified, no attempt to use this for string theory as well. Okay? Yes. So while there's a lot of room out there for trying different things, these are the only things that have worked. So let me tell you, we're not going to try to do this classification. I'm just going to try to give you the list of known symmetry algebras of this form. Okay? They're classified by the number of spin 3/2 currents in symmetry. And roughly speaking, you think of these symmetry algebras that are coming from gauging some invariance involving a field that is coupled to the symmetry algebra. So, for instance, the spin 2 symmetry algebra, spin 2 is the stress tensor. We're familiar with how that came about in the context of the bosonic string. We coupled the theory to worldsheet gravity. And diffeomorphism invariance plus initial invariance, conformal invariance, forced us to gauge set T and T bar equals 0. Similarly, spin 3/2, currents with spin 3/2, like the TFs, come from the equations of motion from gravity. Okay? And you could imagine currents with lower spins, half or 1/2 of 0. Okay, so I'm going to give you the list of all the such symmetry algebras that are known. Many of these we will encounter later on in our study of string theory, not as constraint symmetry algebras for reasons that we'll tell you now, but as global symmetry algebras on the worldsheet, the world sheet of the string, which will imply interesting properties of space. Okay, so the simplest one has, okay, n is the number of gravity nodes, number of spin 3/2 fields. So it's the number of supersymmetries in the action. And a supersymmetry, roughly because we have a spin 3/2 field, you integrate it over Z, you get a spin half charge. Supersymmetry. Okay, so n equals 0, and then I'm going to list the number of fields the number of fields with spin 2, 3/2, 1, half, and 0.
Sorry, when you say symmetrical half integer, what do you exactly mean?
So that the weight of the current is half. Conform the dimension. We're looking at holomorphic fields, so just dimension on one side. Okay, so this one is our familiar friend, the bosonic conformal algebra. So there's one parameter spin 2 and none of all. The other one we studied is the n equals 1 conformal algebra. There's one parameter spin 2, one parameter spin 3 are none of all of these. Now, the simplest generalization of all of these is the n equals 2 superconformal. Several people in this room are very familiar with superconformal algebras and high dimensions. Of course, the analysis algebras also exist in 2 dimensions. Most people in the world are more familiar with the 2 dimensional high dimensional ones. Okay, just a rough recap. You might remember from your study of high dimension superconformal algebras, every time you have a superconformal algebra, you also of enough charge with enough Q's, you also have an R symmetry current. Okay? Now, when D equals 2, the R symmetry current is SON, where n is the number of supercharges. Okay? So, for 1, there was no R symmetry. Because SO1 is trivial, so no R symmetry. But with D equals 2, well, we always just have one stress test. This comes from coupling this thing to supergravity. It's one parameter. N equals 2 is 2, 3 halves. But we have an SO2R symmetry. So you have one R symmetry current. Okay? And you have this. And then there are no. Okay? Now, in addition, more complicated algebras exist with 3, 4, 4, and 4. 3, 4, 4, and 4 supersymmetries. And these more complicated algebras are well, they're complicated. I won't bother describe all of them in detail. If you want. I'll just write down the x, the 3 guy. Okay, this 3 guy, of course, has, as usual, 1 spin 2. And, of course, 3 will spin 3 halves. But it has, can somebody guess how many spin 1 fields it should have? Look at from R symmetry. What should the R symmetry be? 3. Right. And in this case, there's also a current with spin halves. And then not use this. And then there are more complicated things that you go to the equals 4 algebra. Some of these equals 4 algebras do use space-time coordinates. We'll discuss that later. Okay? But as you will see, they're increasingly irrelevant for gauging.
And this go on, right?
Well,
There is no stopping.
no, there is a stopping. There's just 4. This is the full set of known symmetry algebras. Okay, with these properties.
Come on, like supersymmetry algebra will exist for all this.
Yeah. You see, you want not just the global part, but you want this whole local thing with closed domains. So that's a more difficult thing to construct than just the global super. And no known superconformal network to run 2 dimensions exists with higher than this amount of superstructure. Yeah, it's an interesting question, but I'm not personally thought about having to try it. But this is a classic concept. Okay, so fine. So now you might ask, what was the n equals 2 superconformal algebra? Let's try to gauge that. Let's see if we can make a string theory by gauging that. So the thing we're going to do is to now calculate for you what the critical dimension of such a theory is. How do we do that? Well, you remember that when we worked on the bosonic string, we got that the central charge of the coasts associated with the symmetry algebra was three into 2h minus 1 the whole thing squared minus 1. And with a minus sign. Where h was 2. This was the central charge of the BC system with h equals 2. Okay? Now why was h equals 2 there? This is because we had the BC system with we had 2 indices, and where did that come from?
And so this kind of thought of a combination of while and different invariants, but these were while invariant, and since this is so the entire conformal dimension will be given by how it transforms under different, and since here doing this is
exactly. And where did the fact that we had 2 indices come? It came from the fact that the graviton had 2 indices. Okay? And it was tightly connected with the fact that the constraint algebra had 2 indices. Similarly, when we worked out the central charge of the beta gamma system, we got 3 into 2h minus 1 squared minus 1. This was BC, h equals 2. Here, we got a positive sign, and we got this h equals 3 half. Okay? It was beta gamma out of the BC system because the symmetry we were gauging was fermionic, bosonic coasts. And that h equals 3 half? Well, roughly speaking, because the gravity node had h equals 3 half, and tightly connected, they associate with symmetric arbitrarity. So from these 2 examples, you might believe, and it's true if you sit and try to work it out again, that the general formula for the central charge associated with the coasts of a constraint of spin h is minus 1 to the power h times 3 to h minus 1 to the square minus 1 to the power h to h. Okay? Now let's work out these numbers at various values. So first check that we got it right. When h is equal to 2, we got 27 minus 1, so h equals 2, we got minus 26, which is the central charge of the BC system. H equals 3 halves. 2h was 3, so 3 minus 1, 2. So 12 minus 1, then with the plus sign, so we got 11. Remember that minus 26 plus 11 is minus 15, the central charge of the superconformal system. Now what is it that h equals 1? At h equals 1, this is 3 minus 1, so 2 with a minus sign. So we get minus 2. And h equals half. What do we get? At h equals half, this guy vanishes. So we have minus 1. Minus, even though, you would have guessed, oops, yeah, positive. constructed, and finally H equals 0. H equals 0 involves is the same as H equals 1, and gives us the rest. Okay? So, now let's use this to compute the net central charge of the costs associated with the n equals 2 superconformal. N equals 2 superconformal gauge. So, for the n equals 2 superconformal gauge, we get minus 26 from the one spin 2, plus 22 from the 2 spin 3 pass, minus 6 from the 3 spin 1s, and minus 1 from the 1 spin half. Sorry, there's no spin half. I'm sorry. I was mixing up the n equals 3. So plus 22 and then minus 2. Right from the 1 spin. Okay? So we get plus 6. So the central charge, minus 6. So the ghost central charge associated with the n equals 2 gauging would be minus 6. Okay? So in order to make a consistent string theory, if you wanted to, you would have to add in a conformal field theory with charge plus 6. Okay. Now, how do you make a superconformal n equals 2 superconformal field theory of charge plus 6? Well, there's actually, as we will study later on in more detail, a very simple n equals 2 superconformal field theory. The canonical n equals 2 superconformal field theory, just like the canonical n equals 1 superconformal field theory is the theory of a single scalar with a single fermion. The canonical n equals 2 superconformal field theory is a theory of complex scalar with 2 fermions. Okay? And that object then has charge. Has central charge 3. Because 2 scalar fields and 2 fermions give you central charge 3. Okay? So that is a very simple canonical string theory one can write down with central charge 6. N equals 2 superconformal string theory. It's a theory with 4 bosons, 4 fermions, and the n equals 2 superconformal algebra, which is n gauge. Okay, but and it's very important to the n equals 2 structure that the boson in question is complex boson. So n equals 2 supersymmetry mixes bosons in a complex pair. So there are several things about this theory that make it difficult to regard as make it difficult to think of as a sensible string theory. The first thing is that while the theory appears to be sensible in Euclidean space, it doesn't appear to be sensible in Lorentzian space. Because if you try to Wick rotate one of the 4 directions, that would break the n equals 2 supersymmetry. Because the bosons have to be treated in pairs. You Wick rotate one, you should Wick rotate both. Okay? So it's hard to make sense of the Lorentzian theory in this case. Unless you want to theory with 2 pairs. Okay. The second thing about it is that though we've got theory with 4, there's something. At first, this sounds like something is left out, right? Because you have 4 bosons, you've got a theory in 4 dimensions. Think, wow, nice supersymmetric string theory in 4 dimensions. Okay? But, see, problem number 1 is this Wick rotation. Problem number 2 is that although it's 4-dimensional string theory, it does not really preserve, even in Lorentzian space, SO4 invariance. This is because you group your bosons, your 4 bosons, into sets of 2, which are rotated under each other by the n equals 2 superconformal symmetry. So this breaks your SO4 index of SO2 index. Or maybe something maybe exchanging pairs as well. Probably exchanging. Maybe just okay, there's an SO2 times SO2 that's called gauged, and then there's probably an exchange SO2. Okay? But you don't have the SO4 symmetry, global symmetry that you would have wanted to describe a theory propagated up in 4 dimensions. And finally, you're saying that if you had, in the situation where you have one symmetry algebra, one symmetric argument like the stress tensor, that's enough to get rid of 2 degrees of freedom. 26 becomes 24. 26 dimensions becomes 24 because of the constraints associated with stress tensor. It's the usual situation, right? You have one gauge. Before you actually gauge fix, you have one, you can get rid of 1 degree of freedom by gauge fixing, and second degree of freedom because of constraints. Okay? So, you might guess that in this situation where you've got 2 currents, 2 bosonic currents, that would be enough constraint symmetry to get rid of 4 degrees of freedom. 4 scalar degrees. But you started with 4 scalar degrees. And this gets correct. Okay? So, it turns out that if you try to build a string theory with this symmetry algebra, you build a string theory where you have enough symmetry to get rid of all the oscillators, both bosonic and fermionic. All the oscillators. Okay? You don't get rid of all degrees of freedom. There's a 0 mode left, but it's a very small theory. It's a very small theory, and for the reasons that we have enunciated, it's very different from string theories we're familiar with. It sounds so interesting, and while it has proved to have some interesting mathematical applications, this theory of describing 4-dimensional manifolds with complex structure. Okay, it's not had any physical applications. It's not. There's no reasonable conjecture how it connects up with physical landscape. Okay, so although the n equals to gauging by the n equals to superconformal algebra sounds promising at first, it's not proved useful for physics. So it has resulted in some interesting mathematics. Okay. Now you might think, well, n equals 2 is not working very well. What about n equals 3? So now let's see. Let's compute the central charge. Okay, was that clear? Was that discussion of the n equals 2? If there's one thing you remember from this, you should remember the fact that there's a canonical n equals 2 superconformal field theory with a complex boson and 2 fermions. We'll come back to this point later. Okay, we'll discuss this theory in place. Having this structure will turn out to be tightly connected with having space-time zones. Okay, but that's all. Okay, so now, so let's go on. Now let's look at the n equals 3 superconformal. So n equals 3 superconformal algebra, let's compute the central charge. The central charge will be associated first. So minus 26 plus 33 minus 6 and then minus 1. Okay? So what is that? Is that 0? Yeah, 0. Okay, so we get it's 0. So the n equals 3 superconformal algebra is very hard to make in physical string theory. Simply because you can't couple to unit unit. Okay? And for this reason it's proved hard to make a string theory associated with n equals 2 n equals 3 superconformal algebra. And when you go down the list here,
these are the ghost and central charge contribution from the ghost. So you're saying that I cannot a theory with non-zero central charge.
Yeah, you want to describe the theory as propagating something. Strings propagating something. So that propagating theory, at least the way we've done it so far, is a theory with positive central charge. Okay? And the way it works was that this positive central charge plus the central charge of the ghost sector gives you 0. So computing the central charge of the ghost sector tells you what the central charge of your magnetic is. So that was the logic. The n equals 2 theory was the central charge of the ghost sector was -6. So our matter theory had plus 6. Which meant that it was a 4-dimensional theory and then the other. Yeah, this is a 0-dimensional theory. It's a 0-dimensional theory because you can get rid of some of the degrees of freedom anyway. A lot of the degrees of freedom because of the constraints. Basically, it sounds hard to make a non-NP theory out of something like this.
Because the central charge is actually a counter to degree.
Counter the degrees of freedom, and then in addition, you've got a lot of constraints which allow you to eliminate degrees of freedom. So, effective number of degrees of freedom would be limited. Okay? And so on. So, the situation gets worse with the higher algebra. And the next summary is that for the kind of reasons we presented, it is not proved possible to build any useful physical string theory that involves gauging a symmetric algebra that is bigger than n equals 1. Okay. So, while this led us to encounter interesting symmetry structures and we'll encounter global problems, from the point of view of gauging this was a failure. We have not managed to generalize the structure of string theory to gauging high symmetry. Okay, questions or comments about this? We're moving to it. Good. But, nonetheless, even though this attempt failed, you might still want to try somehow or the other to generate theories, to generate additional string theory. And we're going to try something that first sight sounds very weird. It makes perfect sense, perfect technical sense. Physical sense as well, as you see as you know. And that's this. You see, we've seen that the world sheet theories of string theory are always holomorphic. And left movers and right movers largely decouple from each other. Okay? In fact, in the theories we studied, so far, the only coupling has been through zero modes and scales. Okay, so since the left movers and right movers are so largely decoupled, you might wonder, well, why have we been so fixated on treating them more or less democratically? We looked at theories where the left moving sector and right moving sector both were gauged with the bosonic symmetry algebra. And we looked at theories where the left moving sector and right moving sector were both gauged with the supersymmetry algebra. But what about something in between? Something where the left movers are gauged by the bosonic symmetry algebra, whereas the right movers are gauged by the supersymmetry algebra. Okay? Now, many of you are thinking this sounds very unnatural and very weird, but let's try it anyway. It will work well, and more importantly, it tie into the big structure of string theory. So you won't be able to get it, no matter what your prejudices for aesthetics. Okay, so let's try it. So what we're going to do, you can why you don't like it.
So the kind of thing that we initially started off with, we said that there was a string and
Yeah. You go further and further from that point of view. Right. You certainly can't get us to coupling into gravity. Oh, maybe you can in some sense. But not all of it. You can't get by coupling to supergravity. Supergravity, that makes sense. And you can probably get by coupling to gravity, not supergravity. Yeah. So you see that the philosophy is that you start from a natural physical starting point, you encounter a structure, and then you try to generalize the structure to the extent that you can.
But functions already see the space bending in UFP, like T-duality.
T-duality, yes, exactly.
You can very much feel very much part of things.
Well, you see that the space-time physics of these mathematics are not so unusual. But I think Jyotirma was objecting to the fact that we started by taking some natural action in natural two-dimensional action coupled to two-dimensional gravity. The superstring was a little uglier, but you could imagine it as a two-dimensional action coupled to two-dimensional supergravity. Gauging that, and that's where the symmetry algebra comes from. Now, when you start treating left and right very, very differently, the original started. It's harder to imagine such a natural original starting point that will give you the structure. And this I agree with. Okay? But we're not going to let that deter us. We will find all consistent string theories in the sense that all string theories that generate consistent quantum interactions of gravity. If we find such a theory, we will not let our philosophy of what, a pretty starting point for it should have been hinder us. It would be silly to do that. Because, we're in the study of string theory, we are in the same discovery. We don't know the basic principles. So you have to let the theory take you where it wants to take you rather than declaring something. This is what I want to think is good, So that's the philosophy that is permeated the study of string theory. It's not very useful. I think once you follow this, follow let the theory take you where it wants to. Of course, if you try to do something that is wrong, you will hit an inconsistency. And that will be the sign. That will be your sign that your signpost you have to go back. Correct. Or keep it up.
Is there any other way of motivating pedagogy? But it functions. It's often said all string theories are related.
Yes. You see, when you study SQLity, so that would be another way. You see, another way that you would see the type 1 string theory. At strong coupling has an alternate description as heterotic string theory. Now, as we will explain as we get to the study of strong coupling string theory, if you allow yourself to study type 2 theory, there's a sense in which you cannot not allow yourself to study type 1 theory. It's connected along complexes. If you allow yourself to study type 1 theory, if you go to strong coupling, then you cannot not let yourself study that. Because this is the description of that system. Yeah, so that's right. That's if you can't, it will be, if you allow yourself to study one of these theories, you study it in enough detail, you will encounter one of these other theories. So you can't not study it. I mean, if you're interested in the particular description of it, then yes, okay.
What is discussing was if there is some two-line argument on why we have such a weird string theory from type 1.
I don't know what it means.
Generally, this strong pluralities kind of thing, the gauge symmetries get mingled up very actively. This is actually for the same.
The world shape gauge symmetries, right? Because if you have gauge symmetries with propagating gauge bosons, free states, those are negative. So space, in this case, you have free element is free gauge bosons, almost free gauge bosons, and those will be the same. Right, the world shape gauge. Yes. Basically, it's like the theory of B1 brains. At strong coupling in type 1 theory, B1 brains become light. And the effective theory in B1 brains in strong coupling is the theory of heterotic strings. Okay? It's not like the strings of type 1 theory become the strings of heterotic string. As usual. It's the B1 brains of type 1 theory become the strings of heterotic string. Now, why the B1 brains of type 1 theory should have such a weird theory that underlines it.
So the B1 brains themselves do not have very clear.
Well, it's a little weirder in the type 1 theory because of time brains. But you're right. You're right. It's the D1 brains that look into the future. But as we will see, the space-time physics that these heterotic strings give rise to is not weird in any sense. So you should distinguish between the mathematical structures that go into the theory and the physics that comes out of it. The physics in the end of space-time is going to be totally unknown. ago. I don't know better what to say. Maybe people who studied it. None of the people who invented it have better. Well, I don't know. I don't have any idea.
But in some sense, this okay, I just want to understand your comment that in some sense the worksheet is physical. Is there a precise statement there?
Well, yeah, you're right.
Definitely the word volume of D1 plays.
In some sense, the worksheet is physical. And to the extent that it's physical, but you see, the thing that is physical is that part that you get after imposing constraints.
Yes.
Now, the thing that's weird about this structure is the constraints. It's the fact that you have the constraints on one side. Okay, basically, I don't have anything particularly. Let's move on. Okay, I don't think the discussion will take us, especially before we see the theories. Let's see the theories. Okay, so very good. So what we're going to do is to take the left moving side and to gauge the bosonic symmetry algebra. This thing we did for the bosonic string. Take the right moving side and gauge the supersymmetry algebra. The thing we did for the Fermi algebra. Okay, so the left moving side will be C is equal to 26. Right moving will be C is equal to 15. The C hat form, C hat. Now, of course, like with the diagonal theories, there are many such theories, nothing. But we're looking for the simplest, the most symmetric, the thing that preserves maximum space-time symmetry. So, what we're going to do is to choose the C equals 26 theory to be made up of, on the right we will choose the standard superstring. 10 free bosons and 10 free fermions. And we will complete the bosons on the left. So 10 of the 26 units of central charge will be made up by a left moving boson. Okay? So the net field content of our theory will be an ordinary X mu field, both left movers and right movers. Psi mu field, which is only, let's say, right moving. Okay? And then some other C equals 16 theory on the left. Okay. Now, we're not going to try to, basically because I've never seen this done by anyone, we're not going to try to make a systematic survey of all possibilities for the C equals 16 other things. We're just going to try various experiments to see if we can make something that works. I'm not sure if a systematic survey is ever been. You know, we had a roughly systematic survey of possibilities for GSO projections and XZ. One could try to do something similar, to be tougher or something similar here. Okay, we're not going to try that. I'm just going to try, we're going to follow our nose, try to see something and try to make something work.
Sorry, what is this C equals 16 theory?
You see, on the left we have a C equals 26.
Right.
So, part of it is the free bosons. That's equals 10. The remaining part is C equals 16. So we need a completely holomorphic theory with C equals 16.
Oh, it's still in 10 dimensions.
Yes, we're trying to find the theory in 10 dimensions. But the maximum amount of Lorentz invariants. That's how the theory could have. Can't have more than 10 scalar fields because we can't have more than 10 scalars in front. So the maximum number of ordinary scalars will be 10. Okay? So that leaves C equals 16. Okay. So, look, suppose you wanted a C equals 16 purely holomorphic theory. one thing that might have come to your mind is, well, let's look at a theory of 32 left moving particles. Let's try this. Let's try making theories with 32 left moving particles on the left, in addition to whatever you had. In addition to x. Okay? Now, this almost completely specifies our theory. Because we specified the matter content, and we specified what the gauging of things is. But it doesn't quite specify the theory. It leaves it unspecified to the extent that the superstring was left unspecified by specifying its matter content and gauging. Then we have to explain how we deal with the problems. Okay? What structures we're going to allow, and what structures we're going to allow, and what projections we're going to use. So, in the first round, we're going to search for supersymmetry. Now, what property of this worldsheet theory tells us that there's a supersymmetry? This is something I mentioned at some earlier lecture when we have stressed. And that goes this way. You see, if you want supersymmetry, you want some spin 1 current, which you can integrate over the worldsheet to get us so that its zeroth moment around the worldsheet is a conserved charge. That will be your supersymmetry. Okay? Now, you could ask in type 2 theory, what were the currents that led to the supersymmetry system? And the answer is very interesting. Let me remind. I mentioned this briefly, but let me remind you. On the left, okay, on the left, suppose you look at something that on the left is this. Remember? Okay. Let me remind you of the structure of the course in super conformalities. There was beta, which we could bosonize as e to the power minus 5 times 10 beta, and there was gamma, which was e to the power 5 times 10. Okay? And you remember that the operator due to the ground state, operator due to the ns ground state is equal to e to the power minus 5 and had a equals half. And the operator dual to the Ramon ground state was e to the power minus 5 by 2 times the spin operator. The spin operator in bosonized language was e to the power I plus minus h1 by 2, e to the power I plus minus h2 by 2, up to e to the power I plus minus h5 by 2. Okay? This has dimension 5 by 8, this has dimension 3 by 8, so this has dimension 8. Okay, so this is a nice spin 1 holomorphic object. This is a nice spin 1 holomorphic object which can be integrated over the worldsheet. It's not gauged. Unlike TF, for instance, it's not gauged. It represents a global, the integral of this around the worldsheet is a conserved object, which is a globally conserved object. Global charge. It transforms into spinor representation of space-time, because OS is a spinor. Okay? So this object is the object that will represent the supersymmetric charge in our space. The conserved object that comes from the existence of this particular spin 1 current of the worldsheet of the superstring. Okay? Now, on the right moving side of the heterotic theory, we continue to have this structure untouched. So we continue to have this object. Okay? So we are going, since we are searching for supersymmetric theories, we're going to demand, that this operator exists in our theory. Okay, so that whatever projections that we impose in our theory retain this operator. Okay, this tells us two things already immediately. First, it tells us we need a Ramon center. Secondly, it tells us. What a lot about the projections we actually put. In fact, this could have been the way we motivated the study of type 2A and type 2B theory. But I chose not to do it because there was a better way that didn't rely on. I mean, here we're asking for supersymmetry. There we were just asking for consistency. But anyway, asking for supersymmetry, you learn a lot immediately. What do you learn? Well, firstly, this operator exists in theory. So let's say that the operator that exists in there are two sets of spinners here. You can choose any one of them. So if you choose the spinner that has half, then half. Okay. So one of the states has these terms. Okay. Now, we're going to require that all other operators in the theory have single value OPU in the string. Okay? So let's look at operators in the NS sector. Let's look at operators in the NS sector for the right movers. So in the NS sector we have an e to the power minus pi, and then e to the power I m I h I. Okay. The OP of this guy with e to the power I by 2 sum over hi times e to the power minus pi by 2. This OP has to be singular. Okay. The maximum singularity has to be an integer power of z. Now, we've worked these kind of conditions out before. What do we get? From here, from 5 with 5, we get a z to the power minus half. And with m, with these h's, we get plus sum over mi by 2 is from here. Okay? This must belong to integers. But sum over mi minus 1 from here was our definition of the fermion of the NS sector that gets operated. It is the net number of integers behind hi's and phi. So that tells us the fermion number by 2 must belong to integers. So fermion number belongs twice integers. And therefore, it tells us that in the NS sector, we need F projection. Okay? By the way, there's an assumption here. The assumption is that things happen separately on the left moving side and the right moving side. You don't combine the two. We'll find. Anyway, we're working with that assumption. We'll try to relax that assumption later. Okay, so we need a minus 1 to the power f projection on the NS. Similarly, you can ask what other Ramon sector states have single value over units. Okay, so that's a very simple analysis. You have e to the power minus pi by 2 and e to the power I m I h, and then you go into pi by 2 hi power minus pi by 2, and you get minus 1 by 4. That's this guy, plus sum over mi has to be an integer. But you remember that this is equal minus half plus sum over mi was the fermion number in the Ramon sector. Fermion number is minus half plus sum over mi. The fermion number was sum over mi plus the coefficient of the phi. That's minus half in this case. Plus sum over mi. So that tells you once again that f has to belong to twice z. So it ensures that you impose the minus 1 to the f is equal to 1 projection also on the remote sector. Okay? So provided the right moving sector has to work by itself, as single value in so P's work by themselves, the right moving sector, it tells us that if we want to preserve supersymmetry, we have no options. We have to impose the same projection that we did for the superstring on the right moving sector. Okay? Right. So, on the supersymmetric side, we know what we have. We have the same projection as. Thank you. And that's why it comes to choice. So minus half plus sum over mi is twice an integer. Okay. Now, what about the fermions? And let's just remember. Let's just remember one more thing. So, what was the partition function on the right hand side? Partition function on the right hand side was the stuff that came from the bosons plus from the fermions. And from the fermions, we have Z00 to the power 4, and we call this star because it's from right movers. Minus Z01 to the power 4 minus Z10 to the power 4 minus Z11. This was the partition function, the nice modular variant partition. Before? Okay? And remember that the modular invariance is up to phase. In the superstring left, the phase from the left movers cancel the phase from the right movers. But let's remind ourselves what that phase was. I'll remind you of one more thing that we studied in detail. That the transformation of all of these objects. And so then how does this modular invariance work? This guy is exchanged with this guy. Z00 is exchanged with Z01. Z10 is exchanged with Z01. Okay? In the course of that exchange, you pick up this phase, but because these two have a relative minus sign between them, you also pick up a minus. You pick up a minus sign. Okay? You pick up this phase to the power 4. So that was the phase e to the power I pi by 3. Well, because you have minus sign, which you can think of as e to the power minus I pi, the net phase becomes e to the power minus 2 pi I by 3. Okay. These guys just directly give you an e to the power minus 2 pi I by 3. And so the whole thing transforms like e to the power minus 2 pi. Okay? Now, because we're dealing with complex conjugates, to transform the e to the power plus 2 pi. So this whole partition function transforms like Pf of tau is equal to plus 2 pi I by 3 Pf of tau. Well, this is the right hand side, what I call the right hand side. This is the supersymmetric side. Okay? Therefore, whatever partition function we have on the left hand side has to become the opposite phase. Okay? So that will be one of our key constraints. Of course, it has to have its operator product, single value, blah, blah. It must also pick up the opposite phase. So that's going to be our essentially our key constraint. So now what do we do with these 32 fermions? one n partition function can be written for these 32 fermions that will give us this case for the 32 lambda functions. So let's try the simplest possible thing. It actually works. Okay? The simplest possible thing is
all of them the same.
Exact. Good.
Then we can do either. Then we basically have.
Let's write down a partition function.
But the last function is Z1 not.
This is
So we can do both of them. We need either one.
either one of them meaning? Let me show you. It's hard to guess online, but it's very simple to understand this. So we alluded to this when we talked about the probably went too fast. Now, instead to the power 4, we're going to have to the power 16. So 20. Now, the thing that works is sort of interesting. It's just this. All of them with a plus sign. Let's check what this is. Okay. Let's see what phase each of these guys makes. After checking the reverse variation. Let's see what phase each of these guys makes. This guy is e to the power I5 by 3, 4. This guy is same thing, e to the power 4 pi I by 3. And this guy picks up e to the power minus 8 pi I by 3. Similarly to this guy. But the difference between these is e to the power minus 12 pi I by 3. I mean, what I'm saying is that these are the same things. Up to shifts in 2 pi. This is equal to this. These phases are all equal. Different ways of writing the same things. Moreover, this phase multiplied by this phase is also equal. Because it's about 6 pi actually. About 2 pi. That's exactly the right phase. This thing transforms homogeneously and picks up exactly the right phase to cancel the phase of the right pose. Okay? So just in terms of partition functions, this thing works. Is this clear? Okay. Now, let's try to understand what we have. The sum of these two imposes minus 1 to the power f is equal to what? But minus 1 to the power f is equal to 1. Just like in the superstring, even though that didn't have the minus sign. You see, the understanding of that minus sign was that there was a minus 1 to the closest side. The minus 1 to the power f had a contribution of minus 1 from the closed vacuum at the end. That was the explanation of this minus sign. On the matter sector, if you combine the two, you were just imposing minus 1 to the power n. Okay? Here there's no closed sector. There's no superconformal closed. Here you're just imposing minus 1 to the power n. By combining the plus sign. Okay. These two are NS sectors, so we inform that we should be combining NS and Ramon sectors. And what about the Ramon sectors? The Ramon sector has the same relative sign as above here, so it's imposing minus 1 to the power n equals 1. But each of the two Ramon sectors contribute to the plus sign. Now, why is that what you should expect? Why do they contribute to the minus sign?
I think the space-time interpretation of this thing is going to be imposed on us. And it doesn't have clear-cut understanding.
Exactly. The Ramon sector of the fermions, the space-time fermions, guys, the indices of space-time indices, are fermions. And therefore, by the spin statistics theorem, we expected them to contribute to minus. That was beautifully consistent with modular invariance. These fermions have nothing to do with space-time. Their indices are not space-time indices. So the various zero modes that we get by quantizing the Ramon sector will not give rise to space-time spin halves. These guys are the things that we get from the Ramon sector on this side are have the same space-time properties as things you get from the NS sector.
In the modular invariance, they can go be minus.
No. Oh, you see, I only checked the modular invariance under tau goes to tau plus 1.
Oh yeah, there is
Also the tau goes to 1 over tau. I haven't checked, but it requires. It basically requires.
That's because Z0.
Yeah, it's because
Z0 is not being mixed.
Z01 and Z10 being mixed.
So this plus sign should mean that plus sign.
This plus sign should mix that plus sign, and then if you had a minus sign here, you would become an opposite fix. Because these two get interchanged into tau goes to tau plus 1.
Yeah. So
this is supposed to be plus, right, tau plus 1, and then this is supposed to be plus, right, tau going to minus 1. Now, this one is natural convention. It actually at the level of partition functions, this one is some of these three is modular invariant, and this is modular invariant by itself. Okay, and this can be shifted by changing the conventions of what you call chiral and what you call anti-chiral. So that's not an important.
Here I think even that gets fixed. It's a bit better phase. No. You can just put a minus sign.
The minus sign behind. Right. So that's never a serious sign. But just by redefinition, you change that. It's these three that are serious. And these are fixed parameters. Okay? Which ties up very nicely, as we will see, with the fact that these things are not fermions in space time. Okay? And this plus one here, okay, well, that is essentially the statement that that you retain the vacuum sector of your theory. Well, let me say it now. This plus one, if it had been something else, had this been minus one, it would not have been consistently closure of U. Simply because the identity operator simply because well, we probably see this as we check this as we check all these constraints. But the reason I brought this up is that this simple constraint of modular invariance ties up with other nice physical constraints. As is usual, spin statistics theorem, consistency of interactions for closure of the entity. And these are the kind of things that give us faith that something good is happening. Because from one point of view, you get an answer, and that implies something nice from another point. It's tight closures that make us think that something good is good. Okay. Now, so let's look at the words that we associate with this. The words that we associate with this are that the fermions impose the NS one sector, and we impose the UCG of separation. on the matter sector. I mean, usually minus 1 to power f is equal to 1. Okay. Now, let's look at this theory in a little more detail. There are 2-3 things that we'd like to see here. We'd like to see that you have that the OPE is closed, and we'd like to see that operator products are singular. These are the 2 things that we want to check. Both these work. We declare it clean singular. Okay, and it's more or less trivial to check both these properties. Let's see. Let's look at the states in the NS sector. The states in the NS sector are of the form e to the power I, m, I, a. Okay, now I take these fermions and go down into 16 scales, 16 left moving scales, which I call HI. Okay? And as usual, we're very familiar with this. States in the NS sector are operators in the NS sector are objects of this form times derivatives, and objects of this form that have only integer. The MIs are all integers. Objects in the Raman sector are operators of the same form when the MIs are all half integers. Okay? So we've got, these are the NS states. The minus 1 to the power f projection is the statement that sum over mi is equal to e. If we put the opposite minus 1 to the power f projection, we would have got sum over mi is equal to odd. Now that's not closed under the OP. Take e to the power IH multiplied by e to the power IH, you get e to the power 2IH. Sum over mi odd with sum over mi odd to sum mi even. So if you had this minus sign here, that would have not given you a spectrum of operators that would not be closed under the OP. So still interactions. Okay. However, this guy clearly is closed under the OP. Take sum over mi odd even. Multiply with another guy with sum over mi even. The net mi's become mi plus mi prime. Clearly sum over those mi's also. Okay? Good. This is about closure of the OP in the NS sector. Let's look at closure of the OP in the Raman sector. In the Raman sector, we have e to the power I, m, I, h, I, with all mi's being half integers. Okay. But we've got 16 of these half integers. So you add an even number of half integers, you always get an integer. Right. Okay? However, this integer could be of either order even. The integer could be either odd or even, and the minus 1 to the power f projection once again is a statement that sum over mi is even. That sum over mi is even, and that for reasons more or less the same reason we discussed is closed down because sum over mi plus mi tilde is even if mi is even if mi tilde is sum. Okay, so we've got closure under the OP. What remains to check is single valuedness of the no, once we import, you're saying, is it possible for sum over mi to be odd? I think it is possible for sum over mi. Let's check that. Yes. Okay. So each m Fine. So each mi is an odd integer divided by 2.
Yeah, basically, you can write each one of them as j1 plus half. j1 is j1 plus half into j2 plus half.
Yeah, right. Actually, the simple way to see this, let's choose the simplest guy, which is all mi is equals half. That gives you sum over mi is equal to 4. Okay, now flip one of the mi's from half to minus half. That will give you sum over mi is equal to 3. Okay, so it's basically the chirality. The question from the spinner point of view is the chirality. If we stick to all halves or minus halves, the chiral ones are sum over mi is even integer, while the anti-chiral ones are the sum over mi is the other integer. Okay, so we go fine. So, but once again in the Roman sectors, if sum over mi is even, multiply that with sum over mi even, you get sum over mi even. So close up the OP works. What about single valuedness of operator products? Okay, it's basically the same discussion we had in the semester. Let's work it out for the simplest example. The discussion we just had. So suppose all HIs are half. So then closure of the OP will require that half times sum over mi of any other state. Belong is an integer. Right? Because suppose you take the state with half, and then something with m1, m2, m3, m4, you get z to the power m1 plus m2 plus m3 plus m4 by 2. So this thing has to be an integer, which means sum over mi must be an integer, must be an even integer, which is the minus 1 to the power f is equal to 1. So close up the OP works, so then you enforce this projection. And basically, given the existence of such a Roman sector state, it's more or less demand. Okay? Is this clear? Anthony's a bit puzzled. Let's see. Okay. Good. So now we declare victory. We've got a nice theory. It's nice and consistent. We're happy with it. And now we have to investigate. Shall we investigate? No, I don't think so. Okay? You can ask what is BRST coming to the left. Well, it's the obvious one. Obvious BRST coming to the left hand side. The thing you were doing was obviously was content. So the obvious BRST coming to the right hand side. Okay. Fine. So, now let's investigate. By investigating, I mean let's determine the low energy. This theory was supersymmetric. Okay? So, we're pretty sure there should be a tachyon, but let's check it. It was built to be constructed to be supersymmetric. Remember, we demanded the existence of the corresponding space-time supercharge in the version. Okay, but let's check it. So let's try to work out the spectrum first on the left-hand side and then the right side. Firstly, let's look at the right. This is the familiar side, and let's look at the NS sector. In the NS sector, as usual, the ghost e to the power minus 5 by 2 is dimension half. Okay? Massless states are vertex operators with dimension 1. So there's a deficit of halves. So that's the NS sector tachyon. So that tachyon is projected out by the JSO projection. Right? Which demands that demands an odd number of fermion states. Okay? So the NS sector, consistent with the GSO projection, this is the usual story. The states are psi tilde mu. These are massless states. And in the Raman sector, once again we get the usual story. We get negative 5, 2 times the spin operator that we talked about earlier. The spin operators are projected to be chiral by the minus 1 to the power n projection. So we get something that transforms into chiral spinor representation of S of n. Okay? So that's what we have on the right. A vector of S of n, chiral spinor of S of n. That's what we have on the left. Now, by the way, nothing at n0 equals 0. N0 equals negative. No tangent tachyon state because the here. Fine. This is what was on the right. Let's look on the left. On the left, we've got this the vacuum is the no host, there are no superconducting hosts. So we've got our identity operator, which is dimension 0. We need dimension 1 to get it. Here it is instead. We need dimension 1 to get a physical state. And so there are two ways in which we can do it. Of course, we can have alpha mu on 0, the bosonic in the space-time directions, as in the bosonic string. But we could also have lambda 8 and lambda lambda A times lambda, each of lambda A and lambda B is dimension half. This is the NS sector. The NS sector of the Fermat's lambdas. Each of lambda A and lambda B is dimension half. J projection in this case requires the number of lambdas to be even. So this obeys the J projection. The lambda is anti-commuting. So what you get, clearly our theory has a symmetry under SO32. A's and B's can be rotated when SO32 the orbital transformation. Space-time scalar, but under the adjoint representation, antisymmetric and therefore adjoint representation of SO32. Of the open string layers under this strongly covered unit. But at the moment, there are no open strings, no channel. Okay? This is paternal string theory, there are no open strings, no channel. Okay. Now, what about the Raman sector? In the Raman sector, let's look at the dimension of operators. Minimum dimension of operators. The minimum dimension of operators is all of these guys is half. There's no cosine. So that each, the operator you have to write cosines. So you write e to the power I h by 2, h1 by 2, e to the power I h2 by 2, and so on. Each of these components gives you a dimension of 1/8. P squared by 2, so half squared by 2. So 1/8. But there are 16 of them. Some are up, you get 2. So there will be states in the remote sector, but they don't contribute to the massless. It is freedom because you need not to dimension 1 to contribute to the massless. Okay? So the remote sector doesn't give contributions. So as far as massless states is concerned, that's all that there is. We've got the content is what? So now let's see. You've got alpha times this guy, which is the product of two vectors, which gives you the usual graviton, d mu nu, and delta. Okay? Alpha times this guy, so vector times spinor, which gives you the usual radix string spinor and the spin half object, contracting the alpha, in this case, the gamma matrix. Spin half and spin 3 half. This is exactly as in, suppose you had both sides superstring and you replace the alpha here with a sine u, you had indeed get the same things. So this is the usual story. Okay? With the difference that you have only one gravity. Because you don't have the equivalent this spectrum. Okay? So one gravitino, one spin half graviton, maybe one spin half object, and then you've got the graviton, the mu field, and the limit. Usual story. Okay? What's different is this type. This stuff is in the adjoint representation of SO32, and this part is a spacetime vector. You've got a vector in an adjoint representation, massless vector field, an adjoint representation of SO32. You may not be surprised to hear, and we will see immediately as we go on, that these are the vector bosons, and these are the vector bosons that are the adjoint representation of SO32. You've got SO32 gate. And these are the vector bosons with that in the adjoint representation of SO32.
So it's a closed string theory which contains this.
Closed string theory. Okay. And this guy with this guy gives you again in the adjoint representation of SO32. So this is the matter. This is the matter content of an n equals 1 vector multiplet. N equals 1 equals 10 vector multiplet. So the net massless matter content is the n equals 1. N equals 1 and 16 solutions. Minimum order supersymmetric gravitation. So n equals 1 graviton multiplet coupled to a single n equals 1 vector multiplet in the adjoint representation of this. This is the massless content of the set. And given this massless content, the two derivative vector action is completely determined. Just minimal coupling, blah, 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 supersymmetries. Okay? So we understand this theory completely at last. By the way, it's exactly the same massless content as the SO32 type 1 vector. You remember that in the bosonic sector, the SO32 type 1 theory, I should have described this in detail then. You see, you remember that in the type 1 theory, we were in the closed string sector, we were supposed to interchange the orientation reversal, interchange left movers and right movers. Okay? So, of the type 2 spectrum, in the NSNS sector, we have this phi, B field, and graviton. Phi and graviton are symmetric, so they stay. But the B field is antisymmetric, so it's projected out. Okay? Now, however, one should also study the Ramond sector. And I didn't explain this to you in class. We'll probably come back to it. Right? But in the Ramond sector, the only state that survives is the two-form projection. Actually, I didn't even for the type 2 strings, I didn't clearly explain the Ramond content. We'll come back to this. But in type 2B theory, the Ramond content would have been a type 0, a 0 form, a 2 form, and a 4 form. And it turns out that the projection, the orientation projection, I won't pause now to describe why not. Removes the 0 form and the 4 form, but keeps the 2 form. Okay? So the content in the NSNS sector was just as before, was just as here. Namely, a massless 2 form, a massless scalar, and a massless graviton. Those came from different places. You have the ordinary medium field, which is related basically to the fact that under SQLity these strings are fundamental strings. These strings are charged under the Ramon-Ramon form. The fundamental strings are charged under the NS artistic form. So which one gets retained should flip under type 1. This that happens. Okay. And in the open string section, the massless nodes. Well, the gauge goes up. Flexibility the gauge goes up. Plus, of course, you have the supersymmetric rotations when you look at the fermions. That's exactly what you have here. So the massless content of this theory is identical to that of type 2. Is this clear?
Do you have any kind of geometrical feature to this? Like, for example, we could imagine for open strings, we could imagine these kind of individual living at the ends of.
Good. We'll describe a semi-geometrical understanding of this. Compactification and mosaic layers. It's semi-geometrical and we'll describe that in the next lecture. Time. It's a good way. Okay. But now the light is flashing, so let me quickly move on. Okay, so we've understood the matter content of this theory. Is this clear? The massless matter content of this theory, I'm understood the same as the type form. Okay, now let's quickly try to find another way, another supersymmetric electronic string theory that makes sense. I'm going to look at another particle. Let's look at Z00 to the power 8. Square. The net number of powers of Z has to be 16. Let's check that this works before worrying about interpretation. It works because the phases work better than they had to. You took the square root of the phases they also work.
It's 4 pi by 3 and minus 8 by 3.
It has 4 pi by 3 and minus 8 pi by 3.
Okay, 4 plus 8 has 4 plus 4. Even 2 will.
Even a 2 will work. Exactly. Okay? Then of course the overall phase with just 8 is half of what you need, but then if there are 2 factors, you get what you need, you get something else. Okay? So just at the level of partition functions, this also works. Okay. What is the physical interpretation of this? What we're doing is taking our 32 fermions, okay, grouping them up into groups of 16, and individually imposing, allowing these to be individually in NS or Ramon sectors, and individually imposing GSO projection. Okay, so just like for left movers and right movers in the superstring, we allow these things to be in Ramon and NS sectors, independent, left to be in Ramon and NS, independent of what the right is doing. Impose the GSO projection on left movers, independent of what the right is doing. Now, we break the 32 fermions in the left moving side to 16 times 16. You can ask, why did we allow ourselves to do the same with the fermions of the superstring? And the answer is we wanted to preserve the length. But these fermions have nothing to do with space-time. So treating them inequivalently does not mess up the length. Of course, it will mess up this gauge effect.